In the previous class, we have said that in order to achieve population inversion, you will have to selectively transfer population from one energy level to the other. For doing that, you have to actually put energy into the system, into the medium. That means whenever we'll have to create population inversion, you have to dump energy into the system. This is often referred to as pumping the medium. So creating population inversion in the normal parlance is referred to as pumping of the. So there can be number of ways a medium can be, population can be inverted, pumped. Let us first consider the method of optical pump. That means essentially, as the name suggests, this involves employing ordinary incoherent light to manufacture coherent and is generally utilized in pumping solid and liquid lasers. The lasing medium is either solid or liquid. Such mediums are normally pumped optically. This optical light is basically generally obtained from an incoherent, that is conventional source of light, which gives out light. Basically, that light is created as a result of spontaneous emission. So random emission. The photons are all incoherent. They do not have correlation between them. Basically, what you do, you have a medium, suitable medium. You have chosen the medium based on the energy levels. You want to build a laser of a particular wavelength frequency. You have chosen a medium which has the right spacing, the energy levels from which you extract photons and amplify them, making use of population inversion. So you have that medium. And for creating population inversion, you pump it by deriving light from an incoherent source. That means the medium you wrap such a way with that incoherent source of light, that light emitted by the source times this. And you of course use light of right frequency, so the medium can absorb light and you have population inversion between these two, which will come. So you place it inside a cavity and you manufacture a beam of light comprising of coherent. You use incoherent light and manufacture coherent. But the catch here is that while doing that, you lose a large fraction of energy. It is not that all the photons that you are using for pumping the medium you will get back all those photons as water light. No. The efficiency of operation of a laser is never 100%. It is generally much less than 100%. So if you have used, say, 100 photons, just I'm giving a rough idea, 100 photons to pump it, you may get just few tens of photons or even less. So 90% of the energy is lost. So why do you do it? Why do you build this? You are after all losing so much of energy. That is because these are coherent light. And you have used incoherent light to manufacture this coherent light. It has many fantastic properties that can be put to numerous applications in our day-to-day life. Not only in our everyday life, but also advancement of science, many scientific research, medical applications. We have, of course, I have mentioned to you some of the applications that lasers have. So it is because of that you use incoherent light to pump it to make coherent. So optical pumping is one way of creating population inversion. Although generally liquid and gas, liquid and solid medium, lasing medium is ideal for optical pumping, but pumping a gaseous medium is also not uncommon. For this actually to pump a gaseous medium, you see, if you have a gas, there is a lot of empty space between the gaseous atoms or molecules, whatever made up of. If you try to pump it by shining light, most of the photons will escape without interacting with this gaseous atoms because there is a lot of empty space. That is why normally a gas laser is not optically pumped. But as I said, it is not uncommon. So what is basically done is you first convert this incoherent light into a coherent beam of light in another layer, and then use this coherent light as the pump beam. So this is your medium, and you are pumping it by this beam, and you use a means to trap the light inside this so that you can efficiently pump. And of course, it will then lay at another wavelength. So you are basically generating one from one coherent to light, coherent to wavelength, another wavelength. If it is lambda 1, you are generating another wavelength. So in this context, optical pumping can be used for pumping a gaseous medium, this gas laser. Generally, optical pumping is used for pumping liquid and solid. It is more effective because the absorbing atoms or molecules are very closely spaced here to not allow light to escape. Now, so what you do, you shine your medium. I'm showing just for sake of understanding two energy system, and the resonant photons shine this system. The system is at a thermal equilibrium where the lower level less population, and the excited level, the lower level atoms as usual are denoting green color, the excited atom. Now as the photons interacts with it, some of the atoms from this down state will absorb this photon and will climb up. So eventually you have hit a population inverted state, which is of course a state of thermal inequilibrium. A two-level system I've considered here or until now, everywhere I've considered two-level system only for rendering a simplistic view of the process. And we would soon learn that the participation of at least one more energy level is mandatory for the realization of population inversion. The light to optically pump the lasing medium is often derived from a flash lamp that basically, as we have seen, is a fluorescent light source. A fluorescent light source, as you know, is basically a discharge tube, which here is in spiral shape, and you apply voltage, and it works just the way fluorescent light works. We are now familiar with it. So I won't again describe the working of a flash lamp. So you basically use a helical or spring-shaped flash lamp and place your lasing medium, which you want to pump, at the center of it. So for a helical flash lamp, it will be the center of the helix. The entire assembly is often placed inside a hollow cylinder. See, it is placed inside a hollow cylindrical enclosure, possessing a reflective inner surface. The inner surface of this enclosure is reflective. This is to ensure that you see this helical flash lamp, where the light originates from spontaneous emission. So light will be emitted in all directions. So the light which is emitted in the outward direction, if you don't use this enclosure, they will just escape. So this reflective enclosure actually reflects that light back into the resin medium, which is placed at the center of this enclosure. And the light which actually is emitted inwardly, it of course shines the medium equally from all sides. So such an arrangement basically enhances the pumping efficiency. Although flat lamp pumping usually finds application in solid state lasers, its use in liquid laser is also not uncommon. The very first laser, namely a ruby laser, that Mayman operated in 1960, made use of such a helical flash lamp that was wrapped around the ruby rod that used the resin medium. The optical pumping of gas lasers, as I said, on the other hand, is usually accomplished deriving coherent light from a second laser. I just explained. The optical pumping schemes that vary from laser to laser will be described in greater detail when we study specific laser systems. In a majority of gas lasers, excitation of the species from the ground to the higher energy state is achieved by taking advantage of the avalanche of electrons created in a high voltage discharge, much the same way in case of a fluorescent light. But why in gas lasers? Because as I said, in a gas laser, there is lot of empty space. In a gaseous medium, so if you try to optically pump it, majority of the photons will just escape without interacting with the. So what you do actually in a gas laser, you enclose the gas in a discharge tube, and you use two electrodes and create a discharge inside it. The discharge, of course, begins from the stray charges and primarily from the stray electrons, because electrons being lighter will experience much higher acceleration, and thus will acquire more kinetic energy compared to the ions. So the electrons, as they move in this discharge tube as a result of the applied electric field, it will be accelerated, it gains kinetic energy, and thus it will collide with your gas atoms or molecules, which is your lasing medium, and transfer its kinetic energy to the atom or molecule and excite it much the same way as it happens for a fluorescent light source. We have seen it earlier. So that way you actually excite atoms or molecules from the ground state to the excited state. So it's this the scheme is shown here. This is a schematic illustration of creation of population inversion, wherein the electrons in a high voltage discharge, these are some of the electrons are shown here. It has acquired some kinetic energy. Let us assume all of them have some kinetic energy. So corresponding to kinetic energy, they're moving with a velocity v. And initially, it is a thermal equilibrium. So following Boltzmann distribution, it has more population in the ground state and less in the excited state. The electrons in the high voltage collide with the atoms in the ground state and transfers part of their kinetic energy to the atom. So what it does basically, so we call the atom A in E0 state, that is energy is E0. Any electron with a kinetic energy, or we call velocity v, transfers part of its kinetic energy to this atom. The atom climbs to the excited state as a result of this energy transfer to the electron. So this brings atom to upper energy state, and the electron moves with velocity which is less than v. It is less than, because it has given some of its part of its energy to the atom. The atom is now risen to the excited state, and you see the electron now moves with less. So these are inelastic collision, and as a result of this inelastic collisions, some of the ground state atoms are excited to the higher energy level, much the same way as in the case of fluorescent. The electrons after collision moves with reduced kinetic energy, reduced velocity. Now, under favorable conditions, the number of atoms in the excited state may outnumber those present in the ground state, paving the way for the amplification of light. The experimental arrangement to effect electrical pumping for a continuously working laser differs significantly from that meant for a pulse laser, and we will be addressed this in greater detail when we study specific laser systems. There exists other pumping schemes that do not have general applications but are suitable for creating population inversion only in some specific laser systems. The two most popular pumping schemes that we just described now, one is optical, the other is electrical pumping. But there exists some other pumping schemes that are very specific to some particular laser system. One is gas dynamics. Let me explain the physics underneath gas dynamics. Say, suppose you have a system, a medium, and let us focus on a number of blazing number of energy. So this, of course, is non-populated. So it is the best energy state. So this is our E1, E2, E3, E4, E5, and so on. So initially, E1, population of E1 is just, then there will be some population of 2, then E3, E4, E5, they will be practical at some temperature. The room temperature, 300 Kelvin. Now, if you increase the temperature, you heat the temperature to a very high temperature, then what will happen? From Boltzmann distribution law, we know that as the temperature increases, the population of these levels increases. Of course, at the expense of, and in the limit when the temperature goes to infinity, population of all the levels is equal. Suppose we have this population total distributed from this 5 levels. So infinite temperature, if then it will be n by 5. All population of all the states will be n by 5. So basically we are increasing the temperature to increase the population of these levels which are lying higher in energy, which is very scarcely populated at room temperature. So as I increase the temperature, the population of this level will reduce and these levels will increase. But always the population of the lower level will be always more than the one next to it. Otherwise, you will violate the Boltzmann distribution. Now, once the higher energy states have been fairly populated, thermal population, of course, you suddenly cool this gas. So when you cool, what will happen? Again, it will try to come to an equilibrium at that lower temperature. But when it happens, this relaxation, all the energy levels don't relax the same way. Some relaxes at a faster rate, some relaxes at a slower. Basically, you actually mix some other gases with this to ensure that some levels will be faster. Suppose you want to create population inversion between this level, E3 and E2. Now, E3 and E2, E3 also have been populated to a large extent because it is at a high temperature. But you have chosen such a system where E2 relaxes faster than E3. So after the cooling, E2 has quickly relaxed its population and quickly has come in equilibrium, that temperature, lower temperature. This is the T1, this is T2. T2 is much, much less than Q. While E3, it relaxes at a very slow rate. E3 still has much higher because it is yet to relax, come to an equilibrium. So basically, by heating the gas to a very high temperature and cooling it rapidly, you have created a population inversion between these two energies. And now if you put this medium, as you cool it, you also allow this medium to travel in a region where you have placed a cavity. So as this population inverted medium travels through the cavity, he will create, he will be able to amplify light at this frequency because there will be spontaneous emission at this frequency. So some spontaneous emission will be, photons will be there due to spontaneous emission. And the moment you have, there is a cavity, there will be quick to and fro journey of these photons and they will be amplified because you have a population inverted medium. But you cannot maintain this inversion for a long time because eventually it will relax. So such lasers can be operated only in pulsed mode. But you can actually extract huge amount of energy from such. This method of pumping, I hope I have made it clear to you the underlying physics of how you achieve population inversion in a gas dynamic. Such lasers are called gas dynamic lasers, and this method of pumping is called gas dynamic pumping. There is another pumping scheme which occurs through chemical reaction. For example, you say hydrogen fluoride laser. The pumping is done through a chemical reaction. You have, suppose this is your lasing chamber. Here are your gas cavities. And you actually introduce hydrogen. I'm giving you just a very schematic and rough idea. How do you achieve it? Actual, uh, actual case may look very much different. Just to give you a basic idea. Hydrogen and fluorine, they are introduced here and they actually undergo chemical reaction and hydrogen fluoride gas is formed. Hydrogen fluoride is formed. And this is actually formed after the reaction. This is actually formed in excited state. So the ground state of hydrogen fluoride, because here you are only having hydrogen fluoride from here. So the ground state of hydrogen fluoride is there is no molecule in this state, because all the molecule that has been formed is in the excited state to automatically create a population inversion. And because you have a cavity, so you can quickly amplify light. Light, of course, will be again the seed photons will be for the stimulator emission will be the photons originating from spontaneous emission. This spontaneously emitted photons will go in travel in all direction. Now only those two which will travel along the axis, they will only oscillate back and forth, and through stimulated emission they will multiply. Then there is another method of pumping. It is called excimer, automatic pumping in excimer. You see the inert gas like helium, xenon, neon, they are inert. They cannot form a molecule because their electronic structure is full. However, you can form the xenon molecule in the excited state. You excite it, then they actually, the electron, actually when it is excited, it becomes chemically active. And this xenon molecule is formed. When it is formed in the excited state, because ground state doesn't exist. An inert gas, inert molecule, atoms cannot form a molecule. Because ground state doesn't exist, so whatever you have formed, you have actually created a population inverted state. Such lasers are called excimer lasers. All these different but nevertheless specific classes of lasers will be addressed in more detail later in this course. It is also worthwhile to mention here, just for the sake of completeness, that a laser also has been pumped by utilizing the highly energized nuclear particles emanating from the explosion of an atom bomb, from a nuclear bomb. You see, after this nuclear fission, the fragmented particle, fission particles, carry enormously high kinetic energy. And therefore, you once again utilize this energy. You make them, you transfer this kinetic energy through inelastic collision, just as in case of electrical pumping by inelastic collision with electron and the atomic or molecular species that makes your laser system. Here also use the kinetic energy, enormous kinetic energy can be carried by this fragmented particle and transfers this energy to pump your medium. Such a laser, suitable for military application, can give out an intense pulse of laser light before the shockwave, the post effect of a nuclear explosion inevitably destroys it.